points. Okay. So yeah, this is just basics how x86 works. Generally, in the exam you're allowed to ask me a question if you like, right? So it's not clear whether the instruction is left to right or right to left, just ask. Okay? Will usually be specified in the question itself. But if I forget at some point, please don't make a random assumption, just you ask me, right? Yeah, remember how stacks and heaps and data segments are laid out. This is straightforward. Yeah, this is not that relevant. Yeah, then remember how the stack frames work, what goes where, right? On Intel x86, stuff goes down, there are activation records, local variables are here, return address is here. Okay. Then remember that there's a basic code injection attack with a buffer overflow. This is how the attack actually works, right? And you should be able to sort of read a little bit of assembly by now, just a little bit. If I give you in the exam, maybe 3 or 4 instructions should be easy to do, right? So I assume some amount of familiarity with basic instructions on x86. If you want to carry a sheet, welcome. Okay, then format string vulnerabilities. This is a vulnerability where the attacker-controlled value is, for example, going into the first argument of a variable argument system. So therefore, it can have an arbitrary format specified. It's a memory safety problem, right? And you can give values so that things outside of the past arguments can be read. Okay, then this is all spatial memory errors. Temporal memory errors are things which are things like use after free and double free, where objects are used after they have been allocated, right? Or after they have been, freed. So again, the key point to remember here is that to do memory management, the C library has to keep certain data structures. Typically, these tend to be linked lists, because they're relatively easy to allocate chunks to. And what's happening here is that basically, if you have memory that has been freed and you're trying to use it after the fact, then you have no control on how that data is getting used, because it could be writing normal buffer data, or it could just even overwrite pointers sitting next to it, because it's supposed to. There's no, once I free, the memory has no semantics after that. So the program will pretty much allow any kind of writing to happen, right? And this is particularly dangerous because you can go ahead and overflow the buffer and write into neighboring cells. And once you do that, there is a particular set of examples here that I've put out, where you are able to do some really bad things in a linked list. Okay? So you are able to, for instance, manipulate pointers in a way that it gives you an arbitrary write anywhere exploit. The attacker is going to be able to control which location is memory going to be written. Okay? Yeah? And so this happens in a double free. So for instance, you've got a free list in the C library implementation, and you freed a block of data, right? So it's being added to the free list here. And then you end up calling free again on it. And so, this linked list implementation is going to become vulnerable. Yeah, so you just run through this setup. Yeah. The details are not so important in my opinion, but understanding the main concepts is very, very useful. Spatial memory errors and temporal memory errors. Yeah.
So but this one, right? Anything, anywhere, right?
Yes.
Anywhere is only in the heap, right?
No, actually, no.
Stack,
Here.
okay, the code.
Stack. Basically, what's happening here is you have an assignment statement from a pointer to a pointer. Okay. Both are dereferences. And the right-hand side base pointer is also controlled by the attacker. The left-hand side base pointer is also controlled by the attacker. So any value he can read from memory and write it to any value, any destination. Okay? That's what is happening here. Yeah? Okay, the third kind of errors are type errors, things like integer overflow and so on. Again, very straightforward. The problem in integer overflows, the root cause of the problem is that there is no notion of how big or what's the type of value stored in memory. Okay, there's no typing in memory, basically. The language may have types, but the hardware doesn't. And so what happens is, if there is an overflow of values, the interpret those values as negative values or positive values, right, depending on what the type system permits you to do. The basic thing here to remember is, why is this so confusing? Why don't we just design hardware with a separate bit? Well, you can. It's just a historic accident that we chose this particular encoding scheme for all the machines that we have today. They are rather kind of unforgiving. They don't distinguish between signed values and unsigned values explicitly. Okay? And I've put some text out in a document for you to fully understand how counterintuitive this can be. So you can have a program like this one, where it just returns a wrong, completely non-integer result. And these attacks are not just limited to integer overflows. We also discussed how upcasting and downcasting can be exploited in particular ways. If you have an object that's supposed to be, of the base type, but actually it's downcasted if you go from the base to the derived class, and you access that in a wrong way, then basically you'll be accessing memory that's well outside the allocated scope of the base pointer, of the base object. So that's basically the key takeaway. And again, I think there are some helpful links that I've, you can take links here to understand the details of all this, if you really want to get it. Okay, so that's that from the first lecture. Okay, this lecture is primarily about what vulnerabilities show up in these programs. The next one is about exploits, constructing specific bad things to do on these vulnerabilities. Here, I think you need to kind of pay attention to the various kinds of exploits that can happen, and they're slightly different. So you can have a code injection exploit, which is basically a way for you to put some bad payload, the attacker to put the bad payload, and to jump to it and start executing. Also called as foreign code injection. Right? This is a subclass of the total classes of attacks called control flow hijacking. Okay? Right? So there's some details on how this actually works. Right? 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 And then there's some detail about how to handle slight uncertainty or amounts of uncertainty associated with where you're going to start executing the code. And that you handle by an ops line. Yeah? Okay. Now, code injection basically requires these three things to be true for the attacker to work. Right? There has to be some return memory where you can write this malicious payload. There has to be a way to jump to that payload and execute it. Right? And that payload must be marked as executable in memory. Right? And this motivates various defenses, by the way. Those three, you can take out one of those requirements by designing a defense against it. Now, the more advanced control flow hijacking attacks, okay, actually don't utilize all those requirements. They're less stringent. So they actually don't need the attacker to write the payload to begin with. They start with data or code that already exists in memory. Okay, so one example of code reuse attacks is the return, what is it called, the return to libc attack. So the return to libc attack is basically you do the same thing, you corrupt a control flow pointer, but you jump to the beginning of, let's say, a critical system call, like an exec system call. And the point here being that if you can do that, you actually don't have to include your own shell code. You can just put bad arguments to the existing exec code in the program. Yeah. So there's a way to show you how to do that. Basically, you have to set up the parameters on stack, point them to the right places. These are string addresses, right? So they're base addresses of strings, these parameters, and then you just have to jump to the right point and execute. Okay. And then there's this very advanced version of this attack, which is even less stringent, right? And what this is doing is it's basically jumping in the middle of somewhere. It's basically jumping in the middle of instruction streams. And it's doing it so cleverly, this dance, that it ends up jumping between gadgets, as they're called. They're basically jumping between little snippets of instructions, such that the change sequence makes a lot of sense. Okay? Now, how this actually works is the attacker in the exploit sets up certain values in the stack so that after you run the first gadget, it returns to the next gadget starting point. Okay? So those are basically these return addresses that you have to carefully craft. Right? So for example, this is an example of where crafting the return addresses very carefully. And here I'm drawing the stack down. Basically what you do is you jump to the instruction pop EAX, and right after that pop EAX is a return instruction. It happens to be that case. You chose the gadget as such. Right? And when it comes back, it basically uses the return address that you set up on the stack. And this process just recursively repeats. And so you basically end up executing little gadgets that happen to be present in your memory. And the only thing you have to argue yourself about is how likely is it to have these gadgets somewhere in memory. And I basically argued that on x86 systems is very likely because things like return is just a single byte, and things like pop instructions is just a single byte. So, very small byte patterns need to exist for you to find useful gadgets. Yeah. Right, and then what do we have? So this is code injection. Yeah. So looking at how to build defenses, maybe you can mark pages as non-executable. That's one way to defend against this. Right. So one of the things you should do carefully is you should think about which attack requires what requirements, right? And which defense is sufficient to block that attack. Okay, because there are lots of defenses you look at, especially in lecture 3. You've got to kind of have a good matrix of this thing is good enough to stop this, but not this. Yeah. Okay, and then there's a little bit of discussion we had on how to do code pointer integrity, which means how do you protect all the pointers in the program if that's something that's of value to you, right? And the way you do that is the key inside there is not just enough to protect code pointers. You have to protect data pointers that may point to the code pointers. Because if I corrupt them, then I can basically make the data pointers point to code pointers that you just didn't think about. So that's a key idea. Okay, and then there are attacks beyond using control flow hijacking. Okay, so you don't have to just do control flow hijacks. You can just corrupt data elements in the memory, and that happens to be good enough. And one of the kind of most interesting examples of this is, example of this is this particular attack where I'm just corrupting a security critical flag or a value, or turning off other defenses, let's say in the Chrome, in the Internet Explorer browser. So all this requires is corrupting a few bytes of them. Yeah. Heartbleed is another example where actually you don't need to corrupt anything in memory. It's a read error. You give a large enough size and the program is silly enough to print out all the memory that sits next to the buffer. It just prints out all the content that you request, as much size of the content as you asked it to print out. Okay, so that's that, and there's a whole list of kind of hierarchy of defenses, and you should kind of think about which one defeats which class of attacks. Yeah, and this table basically helps you map the capabilities that various attacks need, and horizontally tells you which defense handles which kind of attack. It's kind of a map for you to fully digest. Okay? Okay, so the next lecture is on memory defenses. So now you're looking at defenses. And again, all that is happening in this lecture is we are taking one kind of technique by technique and arguing how it works and which class of attacks it stops. Right? So we look at, let's say, for example, code reuse attacks, right? And we look at various defense strategies. So the first defense strategy is more like an memory access control mechanism, right? Think of it as being the memory safety property where it's got a very specific meaning. Right? Fault isolation says that a module will only access data belonging to its compartment, right? No foreign code policy says that if a piece of code or data has come from outside the system, then it should never be executable. Control flow integrity says that I will decide ahead of time what control flow edges are okay to take, and if I try to execute any jump or function pointer which doesn't traverse one of those safe edges, then I'm going to abort, right? And systems call sandboxing, which we'll also look at in more depth, is a way of saying that I'll allow this program to only run a set of system calls. And code pointer and data pointer integrity says that only code pointers, for instance, can have valid values, should have valid values. Everything else, should have is allowed to be corrupted. Right? And you can limit the scope of pointers to just the code pointers or all the pointers in the system. Yeah, and then basically the rest of the lecture is pretty much talking about how to implement them. Some hardware features, you just go through that. NX is a way of implementing non-executable data, right? Then, then software fault isolation is a way of implementing address sandboxing policies. Right? So the cool thing about this one is a couple of very cool things. One is that you don't have to trust the transformation procedure to implement this. You just have to have a verifier that can check if the transformation was successfully done. Right? So that's a much better design principle. And the second thing is that you've got to be a little bit careful. You can design something which is secure but has a very high overhead. And also you can design something that has a low overhead but may have a bug. Okay? So for instance, here there's a security flaw, and the flaw is that there is a check followed by the real access, but the attacker can actually jump right after the access, right after the check. Yeah. Right. And so to prevent this, there is a particular way of making sure that this doesn't happen. And the specific way of doing that is you use a specific dedicated register, which has a few invariants enforced on it. And the invariants are that that register will always point to the right region of memory, right? The sandbox region of memory. And you can guarantee that no matter where you jump in the sequence of programs, it's always going to be pointing to the right region of memory, and therefore, since that's the only thing being used to access the memory, you're always going to point to the right region of memory. That's an invariant enforcing procedure. Yeah. So just carefully argue as to why this is the case. Sorry, this slide means nothing. Okay, I don't know why I have these slides. I think last time I taught them, I was trying to convey something profoundly intellectual, but it didn't come across as such. Right. Okay. So control flow integrity. There's a way to enforce this. And remember, the big thing here is that you have to estimate ahead of time. You have to estimate what are the valid control flow transfers that should be allowed. In general, this is hard to do. In general, you need to have, it's like solving the hogging problem. But real programs are not the worst case examples. So often there exist good static analysis that let you sort of over approximate the set of valid edges. That's what existing systems use. And once you can do that, the enforcement procedure, there are a couple of ways to do it. Okay? And you basically need to make sure that you're able to do that. Right? So here's one mechanism to do it. And it doesn't protect against return edges, so you need a shadow stack to protect the return edges. But that's pretty much all of that. And so again, it's profound. Okay. So there are some optimized versions of that as well. Okay, so what next? Right. Another very useful defense is address space randomization. So the idea is that the base address of every segment in memory is going to be relocated randomly by an offset every time. That's pretty much it. As long as it has sufficient entropy, the attacker can guess. And then you can do even better. You can randomize the encoding of the instructions, okay? And you can even encode the representation of data in memory by using an XOR value and a secret key inside the processor. Okay, so, and there's some bunch of good practices, protecting against linear overflows using stack canaries, protecting against putting these guard pages between contiguous regions of memory so that if the attacker doesn't know about it, he just hit a guard page and cause the program to crash rather than corrupt large regions of memory. And there are a bunch of useful checking tools. Yeah. And so that basically concludes sort of what we call as hardening defenses. Right? Of course, the holy grail of all this is to just get rid of memory unsafe languages. And so there's something called as memory safety. Right? And to begin to get there, you kind of have to look at how to protect certain types of memory, such as code pointers. Right? So the main argument here is to protect code pointers. You should definitely protect data pointers that point to that code pointer. Otherwise, you're running a big risk. Right? So this point basically talks about why it is not sufficient to just protect the memory allocated for code pointers. You should look at memory that is pointing to it. Right? And then there's a specific definition for memory safety, right? And this is the definition, right? And there's a way to do this, okay, which can be done by binary rewriting, or you could compile it down. And you have to look at three specific properties to enforce for spatial safety, right? And there are a few ways to do it, okay? You can have certain kind of data structures in memory to protect this. The other thing to protect is temporal safety, right? And for doing that, again, you need to enforce these two particular properties. Right? Again, different mechanisms to do it. Various mechanisms can be implemented. There's a lock and key mechanism. There's a kind of a canary-based mechanism where you put a secret value of a reallocate a random value so that if the program tries to access it, most likely default. And some overhead trade-offs between these schemes. Now, any such scheme that you study, remember that you can do it statically or you can do it dynamically. And actually, you can combine the two approaches too. You can do as much as you can statically and leave something to be done at runtime. And so an example of this is this program, which has three different kinds of pointers, something that you can completely dispatch statically, something that you can dispatch with a light amount of instrumentation, called these sequence pointers, and something which requires full-blown safety, memory safety defenses, called wide pointers. Okay, and then we looked at a very different, a much more kind of general property called information flow. Okay. Where what you're trying to say is my program does not mix certain critical values and non-critical values. Okay. Certain input values don't flow to certain output values. That's what you're trying to do. Right? And you have to pay attention to the kind of accesses that you're tracking. Okay, so you have to look at various kind of dependencies that exist between variables in the program. So for instance, if you have a piece of code where even suppose you have a piece of code, if some Boolean value, then x equal to e1 and y equal to e2. Then in this program, there's a direct dependence between e1 and x, because there's a direct assignment between e1 and x. Similarly, there's a direct assignment between e2 and y. Okay? So that's something that things like tail tracking, for example, will track. They will track direct and explicit dependencies. There are also indirect dependencies. So for instance, if you see, there is an indirect dependency between b and x. Because if b is true, then the value of x might change. And if the b is false, then the value of y might change. So there's an indirect influence between the value that b has and the value of x will have at the end of the execution of this fragment of code. Right? So you don't see direct assignment between these things, but there is indeed a notion of influence that b has on y. And similarly, there's an implicit notion. Okay? So for instance, what is implicit? It's also an indirect dependence, but what it means is that suppose b was true. Okay? So suppose b is true. That means x equal to e1 will execute. The else branch will not execute. So should we say that we have a dependence on y? Well, Actually, you should, because had b been a different value, then y's value would have changed. However, if you just look at the path that is executed in the program, you're not going to find any direct assignment between the value of b and the variable y. Because the variable y exists on a path that didn't even run. Okay? But an analysis has to think about whether it should think about variables that exist on paths that didn't even run. So the main thing to recognize here is kind of an important point, is that there are different kinds of dependencies that a little piece of program can create. And typically, you're tracking, in these systems, in train tracking systems, information flow systems, typically, you're tracking just the leftmost top column. Okay? However, your property is often desired to be tracking a lot more. But tracking everything else is a little bit too expensive because you have to think about what happens on branches that index. Okay, so tail tracking, for instance, you can do it statically or dynamically. It's a form of direct data dependence. You're tracking exactly assignments that executed or will execute, for example. Right? You don't track indirect dependencies here. You don't look at the conditional used in a branch and the statements of that branch, if then else targets. Right? Okay, so that's state tracking, and there's a dynamic way of implementing it as well. I won't get into the details. And then there's something called type safety, which is a very general thing, and it can check for things like bad casting errors. It can check for things like integer overflows, and so on and so forth. Okay, and the way this works is you typically define a bunch of type rules, and you say, hey, if this is a following of type B, and if this operation exists, then this must be of type B. Right? And you keep doing this rule, and if you find a violation, you report it to the programmer. You say, I don't know why the hell are you taking a string and a float and adding them up. Right? That kind of stuff. So it's useful. It gets used in the kernel quite a bit. Okay? So that's mostly on defenses. So from the next lecture, I think we switch to doing analysis. Okay? And we did do a little bit of analysis in the previous lecture too, around tail tracking and type checking. So here, we looked at a specific technique called symbolic execution. It's a very, very popularly used technique. And the basic idea is to start with model checking. You start with a particular specification of what is good and what is bad. Okay, the red state and the green state. And then what you do is you look at your program as simply a transition from states to states. Every instruction moves you from one state to another state. Let's say a change of a variable is a change in state. And so all you need to check is there a way for your program to start in a clean state, okay, and end up in a bad state? If there is a sequence of instructions that execute in your program that lead you from a good state to a bad state, then I think you can conclude that this program may have a bug. But if you can't possibly reach from this end of the maze to the other end of the maze, then you can declare that the program is verified to be safe. Right? So this model checking is a way of proving programs to be safe. Okay. The problem is that in this process of creating states, you may skip looking at certain things. You may skip, for example, looking at the variables used in conditions, or you may skip modeling anything but integer operations and log operations. So the fact that you're skipping something, you're kind of making things approximate. And that can give you some false positives in this procedure, right? Because you may think that a particular path is executable because you approximately lost information. But actually when you run the program, you find that the thing that you threw away encumbers you and it actually doesn't drive the execution down that path. Okay. So how do you prune that away? Well, there's a particular way of doing it. You can gather these path constraints. Okay, so you should understand the concept of a path constraint very well. Right? And there's a way by which you are going to use a decision procedure to say, is something feasible or is something not even feasible? Right? It's an arithmetic expression that can't be true. Right? Okay, and then I mentioned that it gets used all the time. There are these decision procedures that do it. And there are various theories in which you write these symbolic form. Dynamic fuzzing, very useful, finds lots of bugs. Actually, nothing to ask you about here. I can guarantee you there'll probably be no question of fuzzing because I don't know what to ask you about. Right, but it just works. Why am I giving the example? Right. But there's this thing which mixes concrete executions with dynamic executions. Very useful again. The idea here is you start with a concrete value, run the program. On that path, you do symbolic analysis. You create path constraints. You do your symbolic checking. The reason why it ends up being very handy is because you don't have to try lots of values that go down the same path. And in fact, what you can do is you can ask very creatively and say, I know this path. I know the set of values that will go down this particular path. I can easily construct a set of values that go down a slightly different path. And the way you do that is you just get your symbolic formula for that path, and you just negate a branch condition which you want to go in the other direction. And how to generate a value that satisfies this? Use a decision procedure, assembly solver. It'll magically take this constraint and tell you, yes, not only is it satisfiable, here is a value that satisfies X, and you can use it to test your program. Okay, so that's how this works. Okay, again, widely used, and that's it. Okay, then we switch to malware. Right. Now in malware, again, 4 different kinds of malware, right? And they can appear at various levels in the hierarchy. Right? So I think you understand the concept of malware. Just remember that they can happen at various layers. Yep, I think where all can they intercept, lots of different places. Then in terms of kind of techniques to, oh, by the way, you should know about what rootkits are capable of doing today. Certainly know what it means. So the most common defense, initial defenses for this were firewalls, okay? And they're basically access control mechanisms. Remember that they go top down. So the first rule is applied first. If that doesn't match, the next rule is applied, so on and so forth. Right? And you have to think about the limitations between a stateful and a stateless firewall. Okay? There's a fundamental difference between the two. And there are attacks that work on the first, but don't work on the front. Okay, then there are defenses which move to the host on the basically on the machine itself, trying to protect the bad program from doing bad stuff, where the OS is okay. So there, we looked at this idea of access control, okay, and this access control matrix that defines who gets to do what. There are ways of creating groups and delegating, and 2 common ways of delegating authority. You can give away a password, that means it's called as authority delegation, or you can basically give the permission by changing an access control list. Unix is an example of a what we call as a discretionary access control system, right? The web is an example of a mandatory access control system. Android is built directly on top of Unix, so literally apps becomes user IDs. The isolation environment is the same. You've got process as a more means of isolating every app. And then again, there are these 2 major classes of policies, right? The mandatory style and the discretionary style. And there's a mix of these called as role-based access control. What we use today is a bit hodgepodge. We basically ask users to decide what policies go for every given app. And really the system is designed to prevent any escalation of privileges after the permissions have been fixed at the time of installation in Android. But there are various attacks that you come later in the lecture that show the limits of this. Right? Now, once you do this, a very nice thing to do is to break up your program into small pieces so that when one of them get infected, you can sandbox that one piece carefully. Right? And the other parts will continue to function. So you can do that. and there are examples of how specifically Chrome does it and how Firefox does not do it. Right? So we look at the details of exactly how Chrome is implemented. Right? Now for reference monitors themselves, you'd like to check some policy on the set of system calls that the program is making. The way you do this is you often want to go for a whitelisting policy, so you specify what is good rather than what is bad. And there are various models that approximately capture a given program set of system calls. The problem here is that this is not enough many times because this model may still permit certain bad things from happening. Okay. What is typically called as a mimicry attack. And the second thing is that there are other issues related to confused deputy. So if I'm analyzing this app, I'm not thinking what this app might do to another app and to make it do its bidding, for example. So that's an example of a confused deputy point. And finally, I just want to argue that this whole idea of asking users to check permissions doesn't seem to work in practice so far. Okay. Yeah. I think the next one is about kernel malware. So here the kind of big sort of things to look at is in kernel malware, what really are your defenses? Right. So this is just repeat. Yeah, how do they actually work? They actually hook in various points in the memory to take control. The mechanisms for preventing this are introspection techniques. So you can run the malware and look from underneath that what changes it's making. Now to do this monitoring, you could be part of the OS, or you could be underneath the OS in a virtual machine. And you can also run separate hardware to monitor. That's also good. Then we look at virtualization. So this is kind of an independently interesting technology because it allows for a whole lot of stuff like isolation and introspection. And the key way this works is through a mechanism called trap and emulate. Right? You basically need to make sure that what was originally running, if it ever tries to access protected memory, you trap on it and then you emulate it. Right? It's a bit hard to do this for x86 because there are certain instructions that don't generate hardware traps, okay, while they're modifying state, which is important. And therefore, for these kind of techniques, you have to use dynamic binary transformations. So you basically intercept on every branch and look ahead of time and figure out which these instructions are and patch them on the fly. Yeah. Okay, so that's that. There are some attacks on this. So there are covert channel attacks, which we discussed. Okay. And that's a way for two untrusted programs to talk to each other. There are side channels, which are very similar, but here the bad guy is observing the timing or the power characteristics or something like that of the CPU, of the program that's running. And we looked at various examples of this phenomenon of side channels, not just on encryption software, but basically in general on any kind of mechanism that's encrypted or trying to hide information. Right, so that's that. And then we saw that the bad guy can put himself below the good guy, and so there's this matrix-like question. Do you want to? The bad guy and the good guy are trying to outsmart each other, so they're trying to figure out who is getting emulated. And there are various techniques to detect whether you're being emulated, and there are various techniques to evade the fact that the attacker is able to detect you. Okay. But this is an ongoing arms race. I don't think this will get solved. Okay, so that's that. Yeah. Okay, so that basically motivates today's lecture, which I think I don't need to go through. But basically motivates why you need to start in a clean slate to end this arms race. And yeah. Okay, thanks a lot. Good luck on the exam. Yeah. And if you have any questions or you want to discuss anything, I'm around.